All right, so we were discussing the theory of constraints, and we came to this definition of a throughput time. Essentially, this is the total time it takes to go through a process from beginning to end for a given job. And we're going to start by looking at the first example and use that to understand a few things about the throughput time, the process capacity, and also in processes that are not purely sequential, like in this case where you actually have a choice of two different paths. Then what can we do in that case? In this particular example, we have this car wash that has two types of wash. You have the standard and the deluxe, and a car goes through a number of different stations depending on its type. Okay, they all go through A1 and A2. The time it takes at each of the stations is given here. You have 5 minutes here, 6 minutes here. Then you have for the standard, okay, it goes through A3, A4, and then to the last station, which is A8, the drying station. For the deluxe, it goes in the other direction. And the questions are: determine the bottleneck for each type of process, the capacity, and so on and so forth. Now, as I have mentioned earlier, if we take each one of these separately, okay, so we take the first path, which is the standard wash process, A1, A2, then A3, A4, and A8. Suppose we don't have any other, cars that are going through the deluxe option. All right. What is the bottleneck for the process? We've already given the criteria. Criteria is the bottleneck is the one that has the largest processing time. And since here we are given times, then which of these is the bottleneck? 5, 6, 12, 15, 10, then it must be A4. So for the standard, it is the A4 is the bottleneck because it has the largest 15 minutes processing time. For the deluxe car wash, if we look at the other path, A1, A2, A5, A6, A7, all the way to A8, the largest processing time occurs here in A6, which takes 20 minutes per car, per unit. The bottleneck is the one with the largest processing time. Okay. How do I determine the capacity from the bottleneck processing time? Well, since the bottleneck processing time is the time between two consecutive finished products coming out of the system, then what this means is the following. Okay, if I take the example that we have here. So we have for the standard, okay, the bottleneck is the A4 is the bottleneck, and it's 15 minutes per car. So to determine the capacity, what do we do? As we did earlier, okay, it's going to be 60 minutes per hour divided by 15 minutes per unit or per car. So this is 4 cars per hour. This is how we determine the capacity. The entire process is based on the bottleneck, and that's why the analysis always starts with determining the bottleneck. How about for the deluxe? A6 is the bottleneck. So for the deluxe, okay, A6 is the bottleneck. It takes 20 minutes per car. And therefore, the entire process moves at the same speed, which means for the deluxe, we can actually do 3 cars every hour. All right, this is how we calculate these values. This is how we get the capacity as customers served per hour or cars washed per hour. if we have percentages now for the entire process, okay, the idea is very simple. Standard represents 40% or 60%. So you have here 60% are standard, 40% are deluxe. To get the aggregate, that means the overall process capacity, it's very simple. We take the capacity of the standard multiplied by the corresponding probability. Okay. Add to that the capacity of the deluxe multiplied by the corresponding proportion. So therefore 4 times 0.6 plus 3 times 0.4. That's how we would determine the overall average capacity of the entire system. Now, how about where you would expect waiting lines? Okay, now I explained this earlier, and simply for each station, if the one before it has a smaller processing time, then there will be a queue. Why? Because it's operating or working faster. So when I look at the standard A1, A2, A3, A4, A6, okay, let's actually do this here in front of you. Have A1, A2, okay, then you have A3, A4, and A8. A3, A4, and A8. This is for the standard. Okay. The times are as follows: 5, 6, 12. The bottleneck 15 and 10. So what did we say? If the step before the one we're looking at has a smaller processing time, then there will be a queue. Meaning, when I go from A1 to A2, it takes only 5 minutes in A1, but it takes 6 minutes in A2. Okay, A1 is faster. So therefore, will there be a queue? Yes, there will be a queue. Because we're processing, or we're washing, or we're processing the cars faster. It only takes 5 minutes. So by the time we finish this one and goes to the second, we finish the second and the first unit is still in A2. So there will be a queue. From A2 to A3, 6 minutes, 12 minutes. We are faster here. So we'll be moving faster than we can process at A3. Will there be a queue? Yes, there will be a queue. Okay, so there will also be a queue here. There will be cars waiting because we are moving faster in A2 than we are in A3. Same thing from A3 to A4. Okay, we're faster in A3 than in A4. So will there be a queue? Yes. Whereas you see when I go from A4 to A8, it takes 15 minutes in A4, but only 10 in A8. So will there be a queue? No. Because, a unit that goes out of A4, it takes only 10 minutes and leaves. The following unit would still be in A4, and therefore, as soon as it is finished, goes to A8, there are no cars waiting. All right. So the way to think about it is simply the following. If the time of the station before it is less, then there will be a queue, because it means it's operating faster. And that's what it says here in the answers. Okay, so A4 is the bottleneck because they all have the longest time in the flow, in the process. The capacities are based on the bottleneck. So once I determine the bottleneck, the capacity is simply the number of minutes per hour, which is 60 divided by 15 minutes for the standard, by 20 for the deluxe. That's where we got the 4 and the 3. 4 cars per hour, 3 cars per hour. The average, just multiply the capacities for each path by the corresponding percentage, 60%, so 0.6, 40% is 0.4. So 0.6 times 4 plus 0.4 times 3, that gives us 3.6 customers per hour. The fourth question was on the steps that would have, okay, a queue, and as we've already said, okay, we've already identified here A2, A3, A4, A2, A3, A4. We're also including A1 because we assume that the customers are arriving faster than we can, operate A1. We're not sure, but we're assuming that. But A2, A3, and A4, we can actually see that because the time is less. Okay. For the deluxe, we can do this here. From A1 to A2, obviously, it's faster in A1, so there will be a queue in front of A2. From A2 to A5, will there be a queue? No, because as you can see, it takes shorter period of time in A5 than it does in A6 and A2. 5 versus 6, so from A2 to A5, there is no queue in front of A5. How about in front of the bottleneck? Yes, it takes, shorter period of time in A5, which is actually the rate of A2, and therefore there will be a queue in front of A6. No queue in front of A7, obviously, and no queue in front of A8, because they all have processing times that are less than the bottleneck. And that's what it says here. For the deluxe, it's only A2, A6, and A1 if we assume that the customers are arriving at a higher rate than A1. Okay. This is the first example, and this example talks about, as you can see, processes that are sequential, where I only have like jobs, but they are sequential. Okay. And there is no sharing, if you will, of the operations. Second example is a little bit more involved. The second example says, what if we have more than one product? So therefore we have more than one job, and these jobs, they share different workstations, they share different operations. So I have 4 jobs, which are called A, B, C, D, and I have 5 workstations, V, W, X, Y, and Z. In each of these, the worker is dedicated and the work a shift of 8 hours each day. Okay. Setup times are considered negligible, so the chart here shows us exactly for each product which workstations are used. So for instance, for product A, it goes from workstation V to Y to X, and it's done. For B, it goes on workstation Y, then to X. For C, it's on W, Z, X, and then Y, and so on. All right. The company can make and sell up to the limit of its demand. The demand is given here. And this is, referring to what we said earlier. We produce what is needed. We don't need to produce what we can produce. We need to produce what we need to produce. Each week consists of 2,400 minutes. Well, where did this come from? Okay, well, it's simply 8 hours. 60 minutes per hour, 5 days per week. That's where the 2,400 comes from. So 2,400 minutes is like 8 hours per shift, 5 days per week. The question says, identify the bottleneck by computing the aggregate workloads at each workstation. And this is where the example is different from the previous one, because you see here, we do not have, sequential steps like here that are very clear and, very well ordered in the sequence from beginning to end. And therefore, I cannot use the rule of the highest processing time as the bottleneck. I cannot, for example, here say that, okay, I'm going to look here and this is 30, so this is the bottleneck. Why? Because station V is, only used by this product, but I can see that Y has only 10 minutes here, but Y is used in every other station, because if you look at this 10, 10, 5, and 5, it's actually 30 minutes if it's used only once by each product. So the idea is, in order to find the bottleneck, instead of just looking at the processing time and choosing the one with the highest processing time, we calculate what is called the workload. Okay. Calculate the aggregate workload for each workstation. That means we find out for each workstation during a given production cycle, for example, here during a given week, how many minutes, how much time will each station be used. The bottleneck will be the one that has the highest time. The way this works is the following. We want to satisfy as much of the demand as possible. So we determine the time it takes to produce or to process each of these products. So for instance, here I have 60 units of product A. Each unit takes 30 minutes in station V. So therefore, in a week, how many will I need? I will need 60 times 30, 1,800 minutes. Do the same thing for instance, Y. 60 times 10, I will need 600 minutes of workstation Y, but this is only for product A. It's also used for B. For how many? 80 times 10, 800 minutes, and so on and so forth. We need to find the loads, which is the amount of time that is needed for each workstation during the entire week, and then compare it to the others and also to the existing capacity of 2,400 minutes. Okay, this is the original idea. How are we going to do this? The easiest way is to do this through this table, where I have for each workstation, calculate the load for each product. The load, as you can see, is the demand multiplied by the time per unit, the number of units times the time per unit. So if I take, for example, X, how did we get these values? I go back to our, example here. Workstation X is used here by product A. How many products? The demand is here 60 times 10. So I will need 600 minutes, 6 times 10 for product A. That's where this is coming from. Then, where is X used again? It's also used here. Workstation X is used for product B. It takes 20 minutes and we have 80 units. 80 times 20. That's where we get the 80 times 20 from. It's right here. And then we have X is also used by product C, right here. 5 minutes per unit for 80 units. And that's where the 80 times 5 comes from here. You see there is nothing from product D because you look at product D, it does not use workstation X. You see W, Z, Y, but no X. And that's why we have 0 in there. So this is how we calculate the load. We do this for each workstation and then look at the total load, 1,800, 1,900, 2,600, and so on and so forth. And we find that the workstation X has the highest load and is therefore the bottleneck. This is what this means. This is how we work this. Okay. It's the highest because compared to all the others, but it's also presenting a problem because it's more than the 2,400 minutes that are available for a given week. And that's why this is a bottleneck. And that's why we call this a bottleneck. This is the other way to find a bottleneck. Therefore, when I have different workstations that are used by different products in a different sequence. All right. So you see, in this case, you cannot just look at the workstation and say, well, the processing time, the highest, that's the bottleneck. It's not necessarily because it is used by more than one product in more than one direction. All right, that's the second example of how to find the bottleneck and obviously determine the overall capacity of the system. Are there any questions on that? Are there any questions on that? Any comments? Is this clear? How we're getting all of these values, how we're determining the loads? I mean, it's not that complicated, but at the same time, if you have any questions, please ask. Okay. That takes us now to the third part of this lecture, which is talking about how can we manage constraints in line processes. How can we manage these bottlenecks? Okay. Now, as we mentioned at the beginning of the previous hour, we said that, you know, when I have a difference between the processing capacities of different operations, okay, like for instance, when I gave the example earlier of, you know, these three that take station 1, 2, and 3, that require 2 minutes, 5 minutes, and 3 minutes. Okay, well, we said that, you know, how do we deal with this problem? If I produce more, you know, at the maximum capacity, I will end up with a lot of inventory that is sitting doing nothing. If I only produce what is needed, then I will end up with workstations that are not balanced, because I will have, you know, one workstation, the bottleneck, working at 100% of the time, whereas another workstation that is working only half or even less than half of the time. So what do? We do what we call here the line balancing. We want to balance the line in the sense that assign the work so that we avoid something like this. Assign the work to the workstations, okay, so that we avoid having a situation where we have a big difference in the processing times. That's the purpose of line balancing. So we want to assign work to stations in a line to achieve the desired output rate. I mean, this should obviously be driven by the desired output. And this desired output typically depends on what we need to produce, not what we can produce, which is the demand. With the smallest number of workstations, at the same time, we want to minimize the number of workstations that would be required. To do that, one, you know, way of, you know, solving the problem is to visualize it, to be able to see it using a precedence diagram. Okay, now precedence diagram, those of you who have taken operations research, and I think most of you have, should look very familiar, because this is exactly the activity on node notation that you used with project managing projects and the critical path method, or the PERT. Okay, it's exactly the same thing, where the activity on node notation is simply that each node represents a task or an operation, and the direction of the precedence is indicated by an arrow. So for instance, if I take this one, it means that S must be finished before we can start T. T must be finished before we can start U. This one, I can only start U when both S and T are complete. This is an assumption, okay? Both tasks S and T must be finished before I can start U. Whereas here, as soon as S is finished, I can start T and U. That's what this means, and so on. So all of these have a different, you know, these are just a follow-up of these. All right. We use this precedence diagram to understand how are the various tasks related, so that I can assign them to workstations, keeping that in mind, because I need to make sure that a task in a subsequent workstation cannot contain activities that predecessors of which have not been done yet. Okay, it doesn't work. So for that purpose, if we take the following example, if we have this example of a manufacturer of garden equipment wants to design an assembly line to produce a fertilizer spreader. They have identified the following work elements. All right. Using the activity on node, let's represent this using a kind of a network. What this is that to understand the order in which these are carried out, I must always start with, you know, the one that has no predecessor. So in this case, it says A has no predecessors. Therefore, I will just have A represented by a node, and there are no predecessors. There's nothing that comes before it. Then you have B and C. Both require A. So therefore, I will have an arrow going from A to B, represented by a node, and one going from A to C, that is represented also by a node. This is what this means. Predecessor, immediate predecessor means that this one must come before this one. A must come before B. A must come before C. Then I look at the following. D and E both require B. You see, D and E both have B as a predecessor. What does that mean? I'll come here and say, okay, node representing D and node representing E. So B is a predecessor to D, predecessor to E. Then you have G and F and G both have C as predecessor. So from C I have arrow going to F and one that's going to G. Okay. H has D and E as predecessors. What does that mean? Well, D and E both point to H. And finally, we have I has F and G. So from F and G, we have arrows pointing to I. This is a precedence diagram, which is exactly the same as a project network. The exact same technique, the exact same way we use it. Each activity is represented by a node, and they are linked together by these arrows. The total time it takes for processing or for assembling this product is 244 seconds. The time here is given in seconds. Okay, this is the time for all of them. Is this the same as the throughput time? Okay, actually it's not. This is just the total time of all of the work elements. This is the same as the one I have drawn here. Okay, so this is why we have A, then B, then C, E, and so on and so forth. This is the precedence relationship. What is given here is the time taken at each of the tasks. So it takes 40 seconds in A, 50 in C, 30 in B, and so on and so forth. Some values that we are interested in knowing. The first thing is, since it depends on the desired output rate, the desired output rate depends on what we desired means what we want. Well, what we desire will depend obviously on the demand. So for instance, if the plan is to make 4,800 units in a given week, and the line operates for 80 hours in a week, then the desired output rate will simply be 4,800 divided by 80. That gives us 60 units per hour. This is called a desired output rate, which is, this is what lowercase r is. Okay, that's what r is. R is the desired output rate. Cycle time is the time it takes. Okay, the maximum time that it takes in one workstation. The cycle time is really the time between two consecutive units coming out of the process. All right, that's what is the cycle time in general. How do I determine that? Well, we can actually determine it in the following manner. Simply 1 divided by the desired output rate. Now here, obviously, the cycle time is in terms of the units of the desired output rate. So if this is 60 units per hour, then the cycle time will be in hours. So when I put 1 over 60, it will be 1 over 60 of an hour, 160 hours per unit. What if I want it in minutes? Multiply by 60. So that will be 1 minute per unit. If it's in seconds, 60 seconds per unit, and so on. Okay, this is how we calculate these values. Then we calculate what we call the theoretical minimum. It's a benchmark or a goal of the smallest number of stations. Okay, ideally 1, but obviously we know that is not the case. How do we calculate it? We take the total time in all tasks, the sum of all of them. So in our example, for instance, it's like 244 divided by the cycle time, which we have just calculated. Okay, so total time required to assemble a unit, all right, which is not exactly throughput time, but let's say it is. Okay, you know. Then you have C is the cycle time. So as an example, if the sum of the work elements is 15 minutes and cycle time of 1 minute, then we'll need 15 by 1, which is 15 stations. Idle time is the time that the system is not operating. All right, like to give you an example, like for instance, if I have in my original example of 3 operations, okay. If I look at this in terms of rates, we said that this is 30 per hour, this is 12 per hour, and this is 20 per hour. We said that if we do not want to produce more than what we can produce at the bottleneck, that means here we're only actually going to produce 12 each hour. Here we're going to produce 12 each hour. Okay. So here when it talks about the idle time is the time that the task or the station is not used. Like for instance here, I'm going to use 12 or I'm going to make 12 in an hour. Each takes 2 minutes. So the total will take 24 minutes. The remainder of the hour is the idle time. The remaining 36 minutes is the idle time. Okay, same thing when I look at this one here. I have 12 units times 3 minutes, so 36 minutes. This is the operational time. How much of the time are we idle? Well, the idle time will be, in this case, 60 minus 36. 24 minutes where the station is idle. That's what idle means. Idle is the time that it's not working. How do I find that out? Simply n, which is the number of stations multiplied by the cycle time, minus the total time. How about the efficiency? The efficiency is dividing the total time by n times the cycle time. Okay. Multiply by 100 to get it as a percentage. And finally, the balance delay is 100 minus the efficiency. So if the efficiency is, for instance, 70%, the balance delay is 30%. That means the percentage of time that the system is not being used. That's what this means. Okay. What does the number of station means and so on and so forth? So if I go back to this example here. Okay. If this is, again, 5 minutes. In this example, n is 3 because I have 3 stations. You see? Cycle time is 5 minutes. Why? Because that is the bottleneck time. That is the maximum time in any station. The sum of the times is like the throughput. It's 10 minutes. 2 plus 5 plus 3. So therefore, if I go back to these formulas here, okay, idle time in this example, idle time will be n times c minus the throughput time. So it will have a total of 5 minutes of idle time in this process. That's what this means. This is what these values mean. Okay. The efficiency is the efficiency of the system. Okay. The efficiency using the values that we have in my example. It's the sum, which is 10, divided by n times c, divided by 15, times 100. So this is like 66 66.67%. This is the utilization. This system will be used 67%. The balance delay will be like the 100 minus the 66. 100 minus 66.67. Okay. That's what these things mean. So N is the number of stations, C is the cycle time. Now, how do we decide how to assign work elements to workstations? Okay. The goal is obviously to put work elements into workstations. So we want to minimize the number of workstations and also make sure that the precedence and the cycle time requirements are not violated. We can use a number of different decision rules for assigning work elements to workstations. Okay. For instance, we can use the longest work element first, or the shortest work element, or the most followers, or the fewest followers. It all depends on the specific example. The main thing is this, that the precedence and the cycle time requirements are not violated, and that the number of stations is minimized. Okay. Now, obviously, we already determined that by determining the theoretical minimum. So the idea in an example would be, I would start by looking for the ideal or for the minimum number of workstations and then assign the work elements to each of the workstations. In this example, all right, for the same, fertilizer example that for which we have the table, suppose that the production line designed to make 2,400 spreads per week, and it will operate 40 hours a week. So it's saying, what should be the line's cycle time, just applying the formulas. To determine the cycle time, I need to determine the output rate. To determine the output rate, I need to take the desired output by the availability. Okay, so that's what we did. 2,400 units per week, 40 hours in a week, so 2,400 R, which is the desired output rate, is therefore 60 per hour. Okay, it's 60 units per hour. So the cycle time is 1 over R, it's 1 over 60, which is 1 over 60 hours per unit, which is the same as 1 minute per unit, or 60 seconds per unit. How do I know that? Because 1 hour has 60 minutes. I can change this in 60 minutes, or 3,600 seconds to get it in seconds. Now, why are we interested in making it in seconds? Because the times are given in seconds. If you go back to the table, you see the times are given in seconds, and we must be consistent when we're using time units. Okay, since this is in seconds, then we must have everything in seconds. The theoretical minimum, just applying the formula, is the total time divided by the cycle time. Total time 244 seconds. We've already found this in the table, remember? That's where we got the 244. It's the sum of all of the times for all of the work elements, divided by the cycle time we computed. Okay, and this is why we need these to be in the same units. So if this is in seconds, this must be in seconds. If this is in minutes, this must be in minutes, which gives us 4 point something. We always round up, so we need to have 5 stations. The question now is, how do I assign these activities, these work elements, to the 5 stations? And the idea is that I actually start assigning from the beginning and move to the right. I keep assigning, okay, until the cycle time is not exceeded or the precedence is not violated. All right. So what that means is that if I start, for example, for workstation 1, the idea is this. I must start with A. It takes 40 seconds. My cycle time is 60 seconds. What are the possibilities that I can put with A? I can put B or C, because once I finish A, I can start B or C. But you see, if I add B, it's going to be 70 seconds total. If I add C, it's going to be 90 seconds total. So we're going to go beyond the 60 seconds, and therefore the first station will only have A. Okay? Because the cycle time is only 60 seconds. I cannot go more than 60 seconds. And then we go on to the next one. Okay? The efficiency was asked for the efficiency, and then, okay, efficiency is simply sum of the times by n times c. 244, we know what that is. 5 is because we have 5 stations, and 60 is the cycle time. We get 81.3%. Now, in terms of the assignment, as I said, of the work jobs to the, or the work elements to the various stations, I've already explained, for example, for the first station, we can only assign to it work element A. Then I go to the next one. Okay. You see, I can either take B or C. You see, if I take B, it will be problematic because with B, I can add to it either E only. All right. However, I cannot add F until I am sure that C has been completed. And that's why we assign C to the second workstation, not B. Again, the same logic. C takes 50 seconds. The possibilities, I could have also B or F or G. Any one of these will take the total time to more than 60 seconds, which is the cycle time, so we cannot do that. So the second station will only take C in it. Then we go on to the next one. Third station, I will have to have B. Then what are the possible additions to B? Well, I could have D, E, or F. Okay, maybe even G. This is where we need to make a decision. Here, of the various possibilities, I chose the one with the highest time that is still within 60 seconds, because 30 plus 25 is 55. Can I add anything after that? We cannot. Even E cannot be added because 55 plus 6 will take us over 60, so we cannot do that. And that's why the third station, the fourth station, will have only, the third station will have B and F. Same logic. The following will be containing D and G, then eventually we contain E and H and I. And you see 1, 2, 3, 4, 5. We have 5 stations in total. And we have assigned, therefore, to each workstation the work elements. And in this case, the line is more balanced than if I just relied, or if we just used each work element as a station. Because you see now, 40 seconds, 50 seconds, 55 seconds, 55 seconds total. And here we have 26, 18, 44, much closer than a difference, for instance, between 40 and 6, or 20 and 18 and 40, and so on. This is the logic of the assignment of work elements to workstations. And that concludes this, quite intensive discussion of theory of constraints. And that's why I took the entire 2 hours to go over this, because there are a lot of details here that I needed to explain. And next week, we'll be spending the entire 2 hours on the exercises, okay, or the practice exercise. Alrighty, my friends, running out of breath. Are there any questions? Is this clear? Any questions on any of this? I mean, if you can do all of this and you have no questions, then honestly, I must, raise my hat up. This is, if you can get all of this, from the first attempt and you get it correctly and you have no questions about it, then you're well ahead of the game. Any questions? Any questions? Any comments? I mean,
no, doctor, it's clear, but we have to practice more to understand.
Okay, thank you, Maimon. All right. Well, you're right. if you look at it systematically, yes, I think it should be, if you follow it step by step. That's why it's a systematic. That's why from the definition we said that, from, the first line, we said that, it's a systematic, which is true. Theory of constants is systematic. There is a system. There are like steps 1, 2, 3, 4. If you follow them, then typically you should be all right. The only thing here is that, as I said, that's why I don't want you to rely entirely on just the systematic, way of doing things, because as a manager, you need to certainly maintain a certain level of common sense, certain level of logic while you're doing this, because sometimes, making a decision doesn't necessarily have to be, systematic. Like, for instance, here between B and C, why did we go with C? Well, as we said, here we are actually we decided on one of the rules. We said, okay, probably the longest work element first. Okay, so therefore, between B and C, we took C. When it came to B, we had like options E, F, or G. Again, we took the longest. Okay, is this the only method? No, it's not. Could we have probably another, diagram for this? It's possible. Okay. So understanding a little bit the logic behind it could be very, very useful. And that, my friends, concludes my story today. I hope you got out of it as much as you could. If you have any questions, you can always obviously ask me or Dr. Riza, and we'll be more than happy to address your concerns. I think this is a good point to stop, and we'll look next week at the practice exercises or the that are given. So now that I have explained the lecture in a little bit more detail, I hope that try to do the practice exercises and then compare to the solution that we will discuss next week. Any final thoughts? Any final questions? Any final comments? No? All right, then.